Okay.
Do you hear me? Yeah, better. Okay, so first the hardware, then a small part on model identification of the Quadrotor. Then there will be a part on wind tunnel experiments that I've performed thanks to the Institute for Fluidodynamics of ETH. Then there will be a part of a small part on the controller design, that a controller that I've used during my tests, and then some simulation results. So first of all, I want to introduce the main goals of the thesis, of the work, and first of all, I wanted to understand what was the importance of wind on a quadrotor. I've seen also yesterday we had the chance to understand that wind is an issue on quadrotors, so we have to deal with this kind of disturbance. Our goal was to estimate wind, so it was not just rejecting wind with a robust controller, but was also to estimate it without wind sensors. So I arrived in Zurich and they say, we don't want to install any wind sensor. You have to be able, if it's possible, you have to come out with an idea on how to estimate wind on a quadrotor with the common sensor that you have on a quadrotor. And so first we have to understand how wind affects the state of the quadrotor. So the hardware in this picture, the main hardware that I've used. So first of all, the PIXOC. So the electronics that we used was the one, of course, of the PIXOC lab. So we used the PX4, which has an IMU and a processor, microcontroller. We were in the PIXOC lab, we had a Vicon room, so we had if I'm not wrong, 12 Vicon cameras, which allowed us to track the attitude and position of the quadrotor. And the frame of the quadrotor, we used the frame of Parrot, so we used the same frame with the same motor controllers and same motors. So I want just to introduce the mathematical model of the quadrotor, not too boring, just this slide is with some formulas. So the model of the quadrotor comes from the rigid body dynamics, so the first equation in the slide. And starting from this equation, you can specialize this equation for the quadrotor, and you arrive to the equation that are in the middle of the slide, so the equation for forces and torques. And with the red square, I highlighted the parts of the model in which I was more interested during my work. Especially I was interested in the inertia matrix, the thrust, the total thrust generated by the propellers on the quadrotor, the force, so the effect of the wind on the quadrotor, so the force of the wind and the torques due to the wind that are acting on the quadrotor due to the wind. And just small remark, DI and TI. DI is the drag moment of the propeller, TI generated by the propeller I, and TI is the thrust generated by the propeller I. Both of them are related, proportional to the square of the RPM of the propellers. And KD and KT depend from the characteristic of the propeller, of course. So to understand wind effects on a quadrotor, this is a picture that I've used because I think it's intuitive to understand it. So if there is wind, the quadrotor is subjected to two main forces, let's say, drag and lift. They have the same expression, but they are perpendicular to each other. So if this is the quadrotor facing to you, the wind is coming in this direction, the lift is perpendicular to the quadrotor, and the drag is in the direction of the wind. Both of them have the same expression, but something is changing, as you say. There is the drag coefficient and the lift coefficient that are different. So if we want to estimate wind, we can understand, okay, this is the drag, this is the lift, but we want to understand the speed and direction of wind. So we have to understand what are those coefficients. It's hard to distinguish between CD times A and CL times A, because the A is the area which is facing the flow of the wind. So at the end, the identification was more the identification of one old coefficient that was CDA and CLA. So these are the equation that we use. And another remark, just to let you know that the thrust, the magnitude of the thrust, is also depending on of course, the input that I give to the motors and to the velocity of the wind, and to alpha, that is the pitch angle of the quadrotor. So to identify this CDA and CLA, we decided to go into wind tunnel. The innovative part, I would say, of this work was that at least I'm not aware of someone who is putting the quadrotor, the whole quadrotor inside the wind tunnel, because we wanted to understand the drag coefficient and lift coefficient of the whole body of the quadrotor. So these are, we made this kind of experiments, so yaw experiments, varying the yaw, pitch experiments, and I took the chance also to identify better the thrust function, so the function that relates the input that we give to the motor to the thrust generated by the propellers. So just to give you an idea, this is the quadrotor mounted in the wind tunnel. On the bottom of the quadrotor there is a an ATI sensor, so it's a force and thrust balance, so it's giving 6 numbers, let's say, force and thrust. So this is the mechanism that allows you to change the pitch and the yaw of the quadrotor. This is the wind tunnel. It's quite big. This is the biggest one that they have at ETH. And just a small remark on the upper right, you can see a wind sensor. A wind sensor, this one is working on pressure, is a pressure wind sensor, and at such low speeds is not working really well. So what we did was using also a knot wire anemometer, so that we bought just for this project. These are the results that we got from the wind tunnel, and you can see that we made three wind. We used 3 wind speeds. The first one is the blue one, 4.7 meters per second, then 9.6 and 12.9. On the x-axis, probably it's too small, but you can understand the orientation of the quadrotor from the picture below. And we had that the trend of the drag coefficient is kind of sinusoidal. So in my opinion, it could be a good result. I think it's more related to the battery, because the battery has the most surface facing the wind, so probably it's related to that. And yeah, the next slide is just to let you understand better the trend. Is just filtered with a moving average algorithm, nothing special. And yeah, this is for the yaw experiments. So we were able to change the yaw continuously. But the problem was with the pitch experiments. The pitch experiments, I entered the wind tunnel. We didn't know before that it was not possible to change the pitch continuously in the wind tunnel. So we had to make just discrete experiments, I would say. So the results that I'm showing here, I'm not so sure about them. So these are the numbers, but I think they have to be validated with other experiments. So what we understood is that the CDA is the drag coefficient. Is a strong assumption, but we can say that it's just a function of the yaw angle and not of the pitch angle. Instead, for the CLA, I cannot say much. We just saw that it's not a great effect on the quadrotor, but I'm not completely sure of that. So we just took an average of the CL times A. And these are the first results that we got from the wind tunnel in the pitch experiments. And the angles that you see on the left, so it's minus 10 degrees is nose up, so nose up of the quadrotor, and 10, 20, and 30 is nose down. The other experiments that we did was to understand the link between the thrust and the wind. So we changed the pitch of the quadrotor, and we gave always the same input, that is this number 375, because we could give an input between 0 and 500. And we noticed that there is a change. I tried to fuse all the results in one function, that is the one that is on the bottom of the slide. And of course, the magnitude of the thrust depends on the input that we are giving to the quadrotor, to the motor, sorry. And then there is a dependence between the magnitude of the thrust and the wind speed, but also to the pitch angle. And these are the results. So another thing at the beginning, I've said that we were interested in the inertia matrix of the quadrotor, because when I arrived in Zurich, there was just a diagonal matrix. So we wanted to prove that diagonal matrix was a good one. At the end, we understood that was quite similar, but not the same. So I made a CAD model of the quadrotor, and that's the result. And you see that the terms out of the diagonal are kind of neglectable. So when you use a quadrotor, the R drawn at least the frame, we can say that the inertia matrix is more or less diagonal. As I said, in the wind tunnel, we also identified a function that relates the thrust, the input to the thrust generated by the propeller. And this is just a slide to show you also the particular of how was mounted the quadrotor on the balance, on the ATI sensor. So you can see the two plates that I designed and also the ATI sensor and the quadrotor on top. So now some words about the controller used. So the controller the controller structure in general was made of two small structures, one off-board and one on-board. I focused my work more on the off-board part, so I designed an LQR controller for the position controller. So it was running on XPC target on off-board with MATLAB and Simulink. And on board there was a PD controller, simple PD controller that I was just tuning time by time for different purposes, and this was the attitude controller. I said LQR based because when you take a quadrotor, we had the chance to change the battery from task to task. When you change the battery, you have a constant disturbance on your quadrotor because the weight is different. So the LQR, if you don't tune the LQR for every battery, then you have the constant disturbance. The other thing that we thought of doing was adding just an integral part to the LQR. Was working quite okay. And so we here in this case, I want just to show you that the difference between an LQR and LQRI really shortly. So if you have no wind, of course LQR and LQRI are working the same. Then if you have a constant wind, this is a strong assumption, of course, the wind is not constant, up to my experience. The quadrotor with an LQR will drift from the position and will tilt. And with an LQRI, it will come back in a tilted position. So just to let you see some experiments, how was the Vicon room and I was working in the quadrotor. So this is with the LQR. When I arrived, you were giving a set point of 1 meter. It was going completely another altitude, but it was pretty stable because the LQR was designed really good in my opinion. So we had a good tuning. So this is the room, was not too big, the one in which we were making experiments. This is with the LQRI. So you see that, now I tried to highlight the integral behavior. So you see that the quadrotor slowly is going to its position. And so it was working okay. And then the last video is about, the last part of the video is about the disturbances. So if you just touch the quadrotor to show you that it was quite stable, and you will see the next. So I was working with the Vicon system autonomously, so there was no one piloting it. So these are just because I think that videos are not so boring as graphs. Before the video, then the graph. So this is the graph related to the video. First, we gave a set point, and we see that the difference is huge. So it's about 0.5 meters. So it's not acceptable. But with this I part, you see that here you have really the behavior of an integral part. Of course, you can make the controller more aggressive if you want. It's no problem. So the last thing that I want to say is just an idea that came to our mind at the end. So we didn't have time to try it too much, so to try it in practice, just in simulation. What we thought is that, okay, I designed also Kalman filter for estimating the velocity from the position given from the Vicon. So I said probably to estimate wind, we can take the state of the quadrotor, extend it with 3 more variables. Now we have 6 variables that are position and velocity. We can extend it with 3 variables that are the wind force in X, Y, and Z, and probably try to estimate it. But you see here, there is here the main problem. So x dot 7, 8, and 9 is equal to 0. This means that the wind behavior is, the wind is as a derivative that is 0, so it's constant, but the wind is not constant. So if you want to follow this approach to estimate wind, you should understand what is the model behind the wind. So you have to at least put something else than 0 here. If this works, then at the end, you, in theory, could have like Kalman position. I called it Kalman position. There is a Kalman observer, Kalman position, Kalman velocity that we already had, and then you can have probably also wind force. And from the wind force, if you have a complete aerodynamic model of the quadrotor, you can go to the wind speed and direction. So, to conclude, this is what I've done. So there is first an LQRI controller. Then there was done CAD model of the quadrotor, an identification of the thrust function, design and extension of the Kalman filter that I've used that tried to extend it. It was working in simulation, so we were able to estimate the wind, but the wind that we gave in simulation was just constant. And then the most important part was an identification of a part of the aerodynamic model of the quadrotor, which has to be completed, for example, with the torques equations. Future, just to conclude, future works. Looks funny, the figure here, but it's kind of an idea also. The first thing is to validate the results in the wind tunnel with the real flight. So what we had was a fan, but the fan, probably most of you know, it gives you not a laminar filter, so it gives vortexes, so you cannot compare the results that you get in the wind tunnel with the results that you get from the fan, because the flow is different. So we tried a cheap idea, and actually it's filtering the flow, not as good as in a wind tunnel. It's an homemade, let's say, wind tunnel. And it was just one of the future work of the work. So I tried to put the quadrotor in front of this structure, and then, of course, going outdoor. Another thing that I noticed during the tests in the wind tunnel was quite interesting. And then after closing my work, I knew that there was also another guy thinking about something like that. Was this thing? So identifying the wind, looking at the current that a motor absorbs, because a motor absorbs more current if there is more wind. So this is another future work, and of course the final goal will be to estimate wind with onboard sensors. That, in my opinion, is possible with a complete identification of the aerodynamic model of the quadrotor. So thanks for your attention. If you have questions. Yep. Sorry, again?
Did you try to plot the drag force versus the wind speed? And if yes, did you get something that was quadratic?
I didn't. So the question is if I try to plot the wind speed versus the drag, right? We didn't do that. So the only results that I have here are these ones. So this sinusoidal behavior between the drag function and yaw of the quadrotor. That's it. Yeah, but I guess that probably the Rayleigh equation works also on quadrotor, but I'm not sure about that. Yeah.
The real wind is kind of random in both speed and direction. If you do the modeling in that force before you put to Kalman filter,
Mm-hmm.
any consideration for variable speed, variable direction?
Yeah. So the question is if in the Kalman filter approach, right? If you have a variable wind speed or wind direction, it can recognize this. It can estimate this kind of wind. I'm correct? Is that the question or not?
You have to model it with the x
Yeah. Yeah, okay, so the model of the wind in that case. In that case, the modeling of the wind has, of course, some uncertainties that you cannot model. It's impossible to model all the wind, but of course, it's not x dot equal to 0, so it's not constant. If you want to assume that it's constant, then you are going to identify probably only the constant part of the wind, but not the uncertainties for sure. If you want to estimate wind in an appropriate way, I think you should go in stochastic theory and stuff like that, that you have uncertainties and these things.
Eventually, you still cannot model the wind because of cannot model the wind.
Yeah, I know that's the main problem. I know that you, but probably you can estimate some part of the wind. You can. I'm completely sure that you cannot estimate wind. Like really short wind gusts, because it's really hard to estimate those, but probably you can estimate what is the wind velocity. So you can take, instead of an anemometer, a quadrotor, put it in the air and understand what is the wind speed and direction.
Any questions?
Yeah.
So why did you choose an LQRI and a PD controller instead of regular PID?
So the question is, why did you choose an LQR instead of PID? The answer is that the LQR is, I would say, is an optimal PID. So when you weight good matrices, then you have an optimal, let's say, PID. That's why. Onboard, there was a PD. I was not really into the onboard controller, but I guess that was just a matter of being as fast as possible and as simple as possible. But the LQR is optimal, that's why I choose it. Of course, there are like nonlinear controllers also, but it was not the topic of the work.
Maybe questions over there? No? Okay, maybe I have one question.
Yeah.
When you fly a quadrotor going front, like gaining some speed, what you see when you pilot manually, or if you look at the integral part of your control, that you have a kind of pitch up effect. Like, it means that when you keep going on banks, your front propeller will finally turn much slower than the one at the back, because you have to push at the back propeller to stay banked. Did you try to measure this effect?
No, this effect was, I don't have to repeat the question, right? No.
Yeah.
This effect actually is really, it's in the future works of the old project. I didn't put on the slide, but this is a nice future work for this work, because it's something that you can understand if you put one propeller in a wind tunnel, for example, and doing the analysis that we have done for the whole body of the quadrotor, you can do it in a smaller wind tunnel with just one propeller. And if you're interested in that, there is University of Pennsylvania, a work of Vijay Kumar that is addressing this stuff.
Thank you.
You're welcome.
Any more questions, maybe? Okay, no.
Okay.
Thank you very much.
Welcome.